Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. This channel provides basics of finite element analysis and computer-aided mechanical engineering design and analysis using CAD-related software. Let's get started.
Hello friends, today I'll show CFD analysis of a Venturimeter using ANSYS Fluent. We'll consider this one as an axis symmetric problem. First of all, we have to start with the geometry and let's select the properties and to convert the 3D problem into 2D problem. Let's close it. Then we have to start geometry. We're starting with new design modeler. Let's select the unit as millimeter and select the plane as XY plane. Let's remove the Z part, Z axis. As it is an axis symmetric problem, let's start modeling from the axis only. Okay, so starting from sketching lines, let's take this one as the axis. Then we can start again the different sections. The extended portion can be deleted or trimmed out. You can trim it. So drawing is complete. Next we can provide dimensions to this one. Let's select the total horizontal length equal to h1, exit end, entry, the distance of the entry and the throat. Let's provide specific dimensions to this one. Let's take h1 equal to 100 millimeter. Let's take v2 equal to 20 millimeter. Let's take L4 equals to 40 millimeter, v3 equal to 20 millimeter, and v3 also 20 millimeter. Now what is complete? Generate. Next one, from these sketches you have to provide an area that will come from concept. Surface from sketches, select any edge of the sketch, apply, generate. So plane is produced. Now select the plane and define the geometry of the plane as fluid. Let's update. So our sketch is ready. Okay. Now next part we have to go for meshing. Let's exit from there. Mesh, edit mesh. This is the drawing. Now before starting meshing we can do something like, while providing input variables, we have to provide names to these different endpoints like entry, exit, etc. That naming can be provided. So we start from naming. As we are considering the edges can be selected from here. This one can be selected as point, this one for solid geometry, this is for plane. We have to select that edges, so we have to select from here. Select that entry and provide a name to this one as entry. Okay, select the exit and provide name to this one as exit. Walls to be selected. You can select both the walls by control and provide name as walls. And the axis is remaining. This one, select axis and provide name to that one as axis. All the namings have been provided. Next one, we have to provide meshing. Initially we have to start with default meshing, generate a mesh. It has provided default mesh, but it is not a good one. We have to refine it. Now while providing meshing, let's select insert and sizing. No selection, we have to select axis. Axis is selected. Now along this axis, as it is 100 millimeter, we have to provide 1000 numbers of divisions to this one. Okay, so what we'll do is we'll select number of divisions to that length and we'll provide 1000 numbers of divisions. And by default the mesh should be hard type, because we don't want any kind of like interference with the software with these meshes. Hard mesh is needed. Okay, this is done. Now at the two entry and exit end also we have to provide sizing. Mesh, insert, sizing, select the edge, apply. Now the size is required, numbers of divisions. This one was actually 20 millimeter. Let's provide numbers of division equal to 40 divisions. And the behavior of this mesh should be hard. In the exit end is also required. Mesh, insert sizing, select the exit end, apply, and the number of divisions, let's provide numbers of divisions equal to 40. And the behavior of mesh should be hard, provided, and these two boundaries are required. Actually we can provide also. We can provide this one later on. Now select the plane, right? Mesh, insert, face meshing, select the face, apply, and let's update the mesh. Mesh transition of Fluent was successful. You can see the mesh. Fine mesh size is there, right? It's very fine. Now how to check the mesh whether it is okay or not? We can see statistics equal to total numbers of elements equal to 40,000 is very good, because total numbers of elements should be varied between 4,000 to 40,000. Where having 40,000 is good enough. Now see other things like orthogonality and skewness also you can check. Let's select aspect ratio of this one. Select aspect ratio. It is okay. Let's see the skewness of this one and orthogonality also. Skewness is okay. Let's check the orthogonality also. Orthogonality is very good. Its value should be 0 to 1. It is lying in the range of 0.97. It's good. Okay. And boundary also, I think it is okay. If you want, you can go for further meshing also, but I think it is okay for this analysis. Okay. Now see the body color. This is the original mesh. Meshing is done, so we can go back to the next section. Let's close it. First update this part. Let's close it. Then we require to set up this initiation. It is a 2D problem and we want double precision. Okay, the Fluent environment is ready. This is our meshed model. First of all, we have to check whether the meshing is okay or geometry is okay or not. Let's check the geometry. It is showing volume and total surface area, etc. It is showing. Let's check the mesh quality. It is done. Maximum aspect ratio equal to 2.04 10 to the power 1. Okay, and it is an axis symmetric problem. Let's move to axis symmetric one instead of planar one. Now let's see the model. This is actually viscous laminar flow, and let's provide material to that one. Material is water liquid and cell zone conditions is fluid domain. Let's see what it is. Fluid domain, it will be having water only. Fluid domain is having water. Okay, next one, we have to provide boundary conditions. That we provided at the entry only. Entry is having inlet velocity in the range of 0.01 meter per second, and we want at the exit it is equal to atmospheric pressure. Okay, and solution methods we are considering as simple method, and let's select the other default values. Next, monitors and residuals. To increase the efficiency of this convergence criteria, we can make this one as 1e minus 6. Okay, let's initialize. With the standard initialization we are starting, and computation will start from the inlet only. Let's initialize and run calculations. With numbers of iterations equal to 1000, we are starting this calculation. It will complete 1000 numbers of iterations. Let's the iterations move on. Calculation is complete. Now we can see results from the graphs. We will see contours, and also it will be contours of velocity and pressure both. Initially we will see velocity, it should be filled. This is the velocity contours. From the color distribution you can see that near the throat only the velocity is very high, and it is maintaining the same velocity throughout the exit. Right, you can see the distribution of velocity. At the entry it is blue zone, and while passing after the throat its velocity is very high. Okay, now we'll see some other thing like pressure distribution also. It is showing opposite trend. At the inlet pressure is very high, and while passing after the throat pressure is less. It is in the blue zone, that means near to atmospheric pressure. Okay, let's close it. Next one, we will see some results in the form of graphs also, right? So plots, we're going to see XY plots, and we're going to see velocity along the axis, let's plot it. right? This is the velocity across the axis. Okay, let's close it. Now I want to see some results or from reports. Surface integrals, facet average. When you see velocity and pressure etc. at any location, suppose when you see velocity at the exit end, let's calculate. It is showing velocity at the exit end equal to this one, 0.024 meter per second. At any location you can see velocity, pressure etc. right? Let's see the difference in velocity at the entry and exit point. So entry point velocity is 0.01 meter per second and exit point 0.02 meter per second. So the difference of pressure is equal to 0.017 meter per second. Similarly, you can check pressure also. Pressure at the entry is 0.95 Pascal and the exit is 0.00329 Pascal. So the difference of pressure between the entry and exit point equal to 0.475 Pascal, right? So this type of calculations you can check from here itself. Now we have to see some flow trajectories of all these particles etc. and to see. So we have to go to the next level. Let's close it. So results, this is our model. We will see in the XY plane only, and this is the default legend view. We want to see first of all, we want to see that contour. Let's select contour 1 and we want to see velocity. Location, it will be periodic show. Let's apply. This is the velocity distribution in a better way. Now we can change a lot of things, like suppose the thing is this color distribution also we can vary. We have some options to see different colors ranges. Here you are having contours colors equal to 11. You can make it more also. Let's see. Suppose you are making more color distribution. You see the colors are also changing from here. So we can have the range of color. It is not only completely red. From red to it is showing to converting to orange color. That means in a more precise way you can see velocity distribution, right? So this is only for one path. We can show in different, that means both the sections also we can check. This is above the axis. If you want to see both, then we have to do some kind of mirroring, apply reflecting mirroring. This was actually in the XY plane, so we have to make a mirror with respect to XZ plane. Apply. This is done. Now we have to make a duplicate contour of this one. Contour 1, make a duplicate of that by the name of contour 2. Contour 2, apply this, that. Now in between we can see that mesh view, where mesh we can remove it. This is the actually path, right? You can see very clearly. We can zoom it. This is the distribution of velocity. The same way you can see distribution of pressure also, right? And also if you want to see more precise velocities, we can change this color notation from a specific range. For more range you can provide for this color. Next part we want to see that vector vector 1, and we want to see locations. It will be periodic show, and the velocity is the variable. Let's apply. This is the velocity in the form of vectors, and we have an option to change the size of these vectors also. Size we can reduce it or increase it also. We can normalize. Let's see. We can reduce the size also as we want. Let's make it 0.62 and let's see. This is the vectors, right? Similarly, like before, we can make the half of that one. We'll show it. Apply reflecting mirroring with respect to XZ plane. Apply. Done. Now we have to make a duplicate view of this vector 1. Duplicate vector 2, and that can be mirrored over here. Apply. Then we can make this wireframe hidden. This is the velocity vector. Now finally we can see the flow trajectories, how these water particles will be moving from entry to exit. That can be viewed. So we're changing this vector 1 and vector 2 we are removing. Finally, we want to see that flow trajectories in the form of streamline. Streamline 1, okay, and it will start from entry. Number of points we are taking 25. Apply. This is the path of water particles it will be moving. Before making that animation, we have to make complete view of this one from top and bottom. First of all, see the bottom part of this one. So we have to change the view. Apply reflecting mirror with respect to XZ plane. Apply. This is done. Now what we want is we want to make a duplicate of this streamline 1, duplicate, streamline 2, that to be mirrored again. Apply. Done. Now this wire mesh, we can make it hidden. This is the actual path of our water particles. Find droplets of water will be moving from left to right following this trajectory. Okay, now let's see the animation of this one. We're going to see the animation of both path 1 and path 2, streamline 1 and streamline 2, and we want to move this one with a very low speed, and this is up to infinity it is moving. Let's change it to 1 divisions only. It will repeat only once. Let's start this one. The water particles in the form of spheres, it is moving from left to right in this way. Now we can do one thing. We can change the design of this one. Instead of these spheres, we can make it to something else. Let's make it in the form of 3D fish. Let's provide the background to be white. Symbol of size, we can make it a little bit more, and the spacing also, spacing in between we can make it a little bit more. Maybe we are making the spacing in between them equal to 0.7, and the symbol of size we are making to maybe 1.5. Okay, apply. Now let's see this one. Fish is moving from left to right. Very nice. We can save this part in the form of an animation also. Suppose we want to save for 2 repetition. Make it 2. Okay. This is all about today's analysis of flow through a Venturimeter using ANSYS Fluent. If you like this one, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.